Um, my name is Vili Lalchite. Today I'm presenting our position paper in collaboration with me, my supervisors, Miguel Cusero, Salviano Soares, and Antonio Valente from UTAD, and the company that hosts me as a researcher, Engenharia from Portugal. Okay,
Click once in the
okay.
Click on the presentation. I'm sure I made it. Took me a while.
Okay. Okay, so this position paper is presenting a cognitive architecture, actually proposing a cognitive architecture for human-robot collaboration in field robotics, and also we are presenting a current state, a work, basically prior work, and a future direction. So maybe you can.
Sure.
Okay, one more. Okay. So when we talk about field robotics, we are actually talking about single or multiple robots that are designed to perform tasks that are physically unendurable tasks for people, for human, because the reason is for that it's requiring and demanding a large amount of human labor and time. Basically, the human would like to avoid to do this. So this is good for the to have the robots in this, especially in unstructured wild environments, and this creates the big challenge because there is a huge uncertainty going on. Basically, these wild environments, when we say it's mostly, we can talk about forestry, agricultural, and construction, and others. And this is the question, then why can't we just remove the humans, and why can't we just adopt robots for all this work? The reason is for that, since these applications are complex and again unstructured, we are still needing the humans' cognitive abilities. And there is also the reason is for that the autonomy level, even we can obtain semi-autonomous machineries or robots. The reason is it is a long life autonomy maintenance is really challengeful. So that's the reason that we still have the human in the loop, and which is a great room to explore for the research, to have a combination of the cognitive skills, empathy, strategic thinking of the human with the robots in this complex environments. And yet we have a lot of actually going great works, especially in social robotics. We have multimodal interactions such as voice, tactile, and gestures. Yet there are mostly peer-to-peer, one-to-one works. And we would like to explore multi-robot, multi-human collaboration, especially in field robotics, because field robotics is more open to have multi-robot system. So this is what we are aiming, especially in my PhD thesis. So I will start to talk about our architecture and the current state. And as the current state, first of all, we would like to have a consistent interaction at the first place with the robot or robots as the end user, which is the human. In this case, we are developing a user interface. Here we are seeing our architecture. We have several components. As we see, robots, this can be different type, that doesn't has to be a homogeneous team. We can have the decision making running FlexB core in as integrated with ROS. Then we have the server, Nakama server, which is a gaming server, as a system coordinator, where we do all this management of the users and the robots communicating with ROS. And we can have also the cockroach database. Basically, if any data should be stored or queried after, we are using there. And then we have the user interface. So at this point, the human is only communicating by using the user interface. And in the future, we will have, as you're seeing there, other type of multimodal interaction. Again, we are, as I told, we have the database and the ROS for the as the software of the communication with robots. And we have Unity, it's a game engine that we are using to develop this user interface. And we have, on the other hand, the Nakama server, which is great to use to have real-time multi-user, multiplayer, and manipulation. So we can have here the overall idea. Basically, we are using the Nakama server as a bridge between these components. We have the user interface there, where the user can send behaviors. When I say behaviors, it's kind of like the task to be performed. All of them are already predefined, and the user can send requests, and Nakama server will do any prior work. For instance, it can be a hierarchical thing, like we can have workers in the field and have one worker has more hierarchy that can ask for teleoperation while the other can't. So these all kind of things are going on controlled by the Nakama server. And these requests after this part is being sent to ROS. Meanwhile, the ROS is, subscribing and publishing several data, for instance, position, pose of the robots, and this is being sent to the user interface, so that not only the pose, actually any battery charge status, any task going on status, and relevant any data to be monitored to the user. And on the other hand, we have the database as, again, to make the query or store some relevant data. Until this point, we developed this not for a research project, but a privately funded project that we have a professional and clients. They are a company that provides service of cleaning, solar panels cleaning with their robots. And in general, what we do is to make it autonomous, and particularly me, I am working on to make this interaction part. And as we see, this is how it looks so far. And you can see there, if you can see the bars, I don't know if it's small, but you can see the Wi-Fi signal. This on the top, the green robot is selected. When you select it, means it's there. When you select any robot, it will show off the all the relevant data, and you can see any operation that you can perform. Okay, is the video okay? For instance, for this specific project, there are several behaviors tasks to be performed. So the user can clean the panel, whole panel, or the user can choose to teleoperate the robot or autonomous. So teleoperation is something, and these cleanings are all autonomous. And you can clean, try to clean all the panel or clean the panel along a previously recorded path. And you can, by the way, see the cameras as well. And the robots can go to the dock position to get charged. And this is also a behavior that you can request. And also, this is called as dock and undock. And you can as well record a dock and park and pet and panel. So basically, all of these things can be requested by the user interface for that time or for a schedule for ahead at any time. And we can represent a very preliminary result, representative result. Basically, our client was asked to do the daily job that he every day do the experiment. We asked that if he could do everything he does with the UI, and the results are the questionnaire that he did is basically shows that the consistency and the system monitoring is good to have, and better than what he was having before. But on the other hand, it is yet not affecting any working performance. So far, it is what we just wanted to provide until this point is just giving a monitoring and the consistent interaction. All of this will be used as one type of interaction. Thank you. So feature direction. After this point, we will be talking about what we propose to go from here to a proactive human-robot collaboration. So when we talk about proactive human-robot collaboration, the researchers from not only from robotics, also from cognitive science and psychology, they had made searches and they came up with 3 criteria: what, when, and where. So what stands for what are the intentions of the other agents? When I say other agents, I mean other robots, other humans. And then acting accordingly to this behavior, and then where to perform this joint action, because when I mean human and robot joint action, and how to perform and when to perform. These 3 things are basically these spatiotemporal key is the essential for any human-robot collaboration, and this is what we would like to explore as a feature direction. And there are issues, of course, because when we think about all of this requires continuously being self-aware of the robot and surrounding environment, and these are computationally a bit demanding. So what we would like to also try to tackle this problem, because it will eventually need a storage capacity, which also limits the mobility and reduces the weight. So to tackle these problems, we are proposing a human-like decision-making modeling with enhanced finite state machines to tackle the uncertainty level of the human, and spatiotemporal decision-making with multi-agent deep reinforcement learning. And in the end, we would like to explore the knowledge transfer and distributed processing with fog-enabled federated learning. The first step we will try is human-like decision-making. When we are putting the human in the having the human in the loop, we would like to know what is the next step, what will be the intention of the human. So in order to have this, we have to consider the uncertainty of the human, since we are not machines, we don't know what the human will do. And to do this, there are great works out in the state of the art when we take a look. But we would like to explore the finite state machines, which is great to model the dynamic events that change over time. And there are works that enhances finite state machines with the physiologics. And basically, the great thing is that they are modeling the transition between the states. The states are basically the behaviors, current behaviors, and the transitions are basically modeled with the physiologic that is giving the ground truth of the what will be the next step. And what is great about this, although there are works about probabilistic methods, the great thing with the using the physiologic here is with this ground truth thing, it can be a multitasking, because at one time it can output several or more than one at least output. That is good to have a multitasking, which can be important in decision-making system. That's why we would like to explore this. And our contribution would be here, having multimodal interaction in this part, because we believe that would certainly reduce the uncertainty level of the behaviors. For instance, here we can see a work that is in order to make a model of the human in daily activities. They have been using this finite state machines, and they enhanced it actually with LSTM and CNN in order to have the time dependency as well. And this work actually is great, but however, they have been using only the mobility sensors, and we would like to have go beyond of this with this multimodal interaction. This would definitely give, for instance, we can use heartbeats and kinematics, and as well this explicit communication that we just saw before here in our prior work, which is this user interface. Okay. And the second step is spatio-temporal decision making. We would like to have if we are talking about multi-robot, multi-human, we would like to have the multi-agent decision making. In order to do this, we would like to have this graph theory, graph neural networks, which is basically you have the nodes representing the agents, and the edges between these nodes representing the relationship. So it is kind of modeling the environment, considering the relationship between these agents. And these relationships can be modeled as explicit and implicitly. Explicitly means like this user interface, like very explicit communication is going on, that you can command on the robot, can come up with a plan and assign a task to another robot or to the human even. And implicit communication, implicit relationship is more than a proximity related thing. Basically, for instance, when a human is needing an assistant, only the distance closer robot will go to provide some assistance. So all these things should be considered. That's why we would like to explore the graph neural networks and extend it with the previously input of the FSM, basically to have the output of the human in considering the uncertainty of the human level. And finally, when we are talking all of this, this is basically storage, computing, and demanding a powerful computational burden. So we would like to explore folk-enabled federated learning here. When we say federated learning, we would just would like to have distributed machines that only exchanges the parameters, not all the things, but only the parameters. That will be definitely good. But on the other hand, it still suffers from the communication, and that's the reason. With that reason, we would like to have a fog-enabled federated learning with having several local machine server going on, and this is what we in the end want to have. And even this created model could be in the cloud. That's another setup in another somewhere could have used this learning the trained model. So this was the future work what we would like to have in the current state. I hope in the next years, I would like to have addressed these issues with good results. Thank you very much. Also, sorry, I have this conclusion that I need to say that we would like to have in the short-term steps. Currently, we are working on a simulation where we would have the humans avatars basically going on and the robots. And if we could have the avatars controlled by several players and using their joint data and train this joint data to use in order to use in this first step having the modeling the human behavior. This could be good in the future for the community because, as we know, having this data sets is even creating a data set sometimes can be time consuming, and even thinking about the sensory and everything equipment can be even expensive. So we will see how we could go far to have a very realistic data, joint data, and if we can manipulate and if we can even make it plug and play, so other people could make several animation, but not clip like procedural animations. This is currently what we are doing, and yeah, so this is it. Thank you. Is there any question?
Okay, so also if we are a little bit